Okay, welcome everyone to our Zach seminar, and today is my big pleasure to introduce my friend Julius Ross from Chicago, and Julius will speak about Hodge-Riemann classes and Schur polynomials.
Awesome. So thank you, Vanya and Jesus, especially for the huge work you put into Zag. I'm technically an organizer, but really it's their deal. So this is a wonderful seminar, and I'm going to speak about this joint work with Matej Toma that we've been doing over some years now. So it has some old things and some new things as well. Let me start by just telling you some pieces of the classical hard-Lefschetz and Hodge-Riemann bilinear relations that I'm sure is familiar to many people on this call. So the setup is we'll always have a, say, compact manifold. I'll work over the complex numbers of dimension D, and I'll also fix some positive class on X. So for example, you could have either omega is C1 of some L, where L is an ample line bundle. Or if you don't want the projective case, you could have omega as a Kähler class. Right, so both of these work, and I'll need both of them, right? So I've just said those. And then there are these two statements. The first is a particular case of the hard-Lefschetz theorem that says if you take this map going from the 1-1 cohomology on class, 1-1 cohomology classes on X to the D-1, D-1 obtained by wedging with omega to the D-2, then this is an isomorphism. So as long as you need this positivity, and then you get that this is an isomorphism. And then, a refinement of that is you can identify this space with this space using the natural pairing. And then this map becomes a bilinear form on this space here. So I can write down this bilinear form, which I call Q, obtained by, if you take two 1-1 classes, you can just integrate them. I've missed out the sort of wedge product here. You take the wedge product of these classes. So this is a top degree class on X, and you integrate it. And the Hodge-Riemann bilinear relations, or this particular case of the Hodge-Riemann bilinear relations, say that this has a particular signature. So it has signature plus, minus, minus, minus. So you can diagonalize this Q with respect to some basis, and then it has this particular signature. So I call this signature either Lorentzian, or sort of Hodge-Riemann type, or something like that, if I want to refer to this particular kind of signature. Okay, so that's a classical statement that many people know. And then the question that I think was initiated by Gromov was to say, okay, you've got this omega to the D-2 here, that's coming in twice, the same omega to the D-2. And so the question he asked is, can this be replaced? So can we replace omega to the D-2 with some sort of other class, let's call it capital omega, that's going to be a D-2, D-2 class on X, right? So, by which I mean you replace it, and you hope to have analogous properties of hard-Lefschetz and Hodge-Riemann bilinear relations. Okay, so let me make that clear. I prepared this. So let's say you've got some class, this D-2, D-2 class, and I'm always going to assume it has some small amount of positivity. So let's always assume that if you integrate that against the square of some positive class, it's positive. I don't want to allow you to take kind of minus the class, right? So this is asking for some positivity. And I'm going to say this has the hard-Lefschetz property. If this map here from H11 of X to H D-1, D-1 of X obtained by wedging with omega is an isomorphism. And similarly, I'm going to say it has the Hodge-Riemann property. If you can take this bilinear form, which I'll call Q omega, again, you pair it with two 1-1 forms obtained by integrating alpha, omega, alpha primed, so alpha and alpha primed are 1-1 forms. If this has the same signature plus, minus, 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 right? Okay, so that's what I want to have, and these cohomologies are all over the real, of course, right? Great, and I'll just let HR of X be all the classes that have this HR property. And so, Gromov's question is essentially, can you find other classes, or can you describe what this is, or can you describe all such classes? All right, so so the silliest example is the one I've already given, right? If I let omega be the first term class to some power, or a Kähler class to some power, then this has this properties. These two things, these imply that omega has this Hodge-Riemann property. So that's the classical statement. Here's an example that's due to Gromov, at least in some case, and then maybe Din Nagoyan, who worked on this, said we can take not just one positive class and take its self-intersection, but we can take several different ones. So he said I can take omega to be little omega 1, which omega 2, which omega to the d minus 2, say where each omega I is a Kähler class. So if you want, you can just think of those as projective class. Then this has the Hodge-Riemann property on X. So again, that clearly generalizes before, and the proof is actually not just a consequence of this statement, but it's sort of similar in spirit of proof. And then the second kind of example is a theorem due to Bloch-Giesecke, and that's related very much to what I want to talk about today, that has to do with ample vector bundles. All right, so the statement is this: I suppose you've got an ample vector bundle on X, its rank should be large enough. Then this class here, CD minus 2, has the hard Lefschetz property. And so let me just recall some things for you. So let me recall, because I'll use it, that E is ample means that if you take the tautological line on the projective bundle, this is an ample line bundle. And I won't try to put in the proof of the Bloch-Giesecke theorem, but not a surprise, what you do is you apply the classical hard Lefschetz theorem on this space here, right, on P of E, right? So you've got to do that in the right way, but you take P of E, you have this class here that is positive, so you have the classical hard Lefschetz theorem on P of E, and then after some manipulation, you get that this thing has the hard Lefschetz property. So it's not so hard, and that's also a classical thing. And as far as I know, that really covers all the examples that were known before our work, or at least all the general examples were just sort of these three things. And with that in mind, I can just state maybe the first version of our theorem, which, as from the title, is going to be that Schur classes have this Hodge-Riemann property, right? So let me define what those are before I state the theorem. So again, I need some notation. So suppose I have an integer E, which is going to be the rank of my vector bundle E. And I have a partition, so that's an increasing number of integers, and they sum to something. So this is called the length of lambda. Right. And then the Schur class of E is again just some characteristic class of E that you can obtain in this way. You take a determinant and you put the Chern classes of E into the determinant in this particular way. So you put the lambda 1 Chern class, the lambda 2 Chern class, lambda n Chern class along the diagonal, and then you increase by 1 as you move along a row, and decrease by 1 as you move along a row the other way. Okay, so this is maybe not the most enlightening definition of what the Schur polynomial is, Schur classes, but it's sort of just efficient. It's just some combination of Chern classes, right? And if you look the way I've written it, this thing lies in H mod lambda of X, right? And so you can think of this as a characteristic class, or if you want to think of it as a polynomial, just remove the E's everywhere, right? And then by C here, I mean symmetric polynomials. And then again, this is just some symmetric polynomial in E variables, right? So you can think of this characteristic class as being that symmetric polynomial of the Chern roots of E. So I'm going to think of these as polynomials or as characteristic classes freely. And I just gave some example here. So if you take the partition of 3, so there are 3 partitions of 3, I can take 3, 0, 0, 2, 1, 0, 1, 1, 1. There's the non-trivial ways of adding up to 3. So the first one is just the usual Chern class. The last one you may recognize is the Segre class of E, and you always end up with the Chern class on one extreme, the Segre class on the other extreme. And then there's this middle one that just happens to be this combination here of C1, C2 minus C3, right? And you can work for any given partition. In principle, you can work out what this polynomial is in terms of the Chern classes. Very good. So with that, I can at least state our theorem. So this is with Mattei-Thoma. So again, as I just said, we're going to have an ample vector bundle. It has rank E. The rank should be large enough compared to the dimension to avoid trivialities. we have a project on an X of dimension D. We have one of these partitions of length D minus 2. And then the conclusion is that the Schur class has this Hodge-Riemann property. So let me just spell this out because it's the main theorem. If you take this bilinear form obtained by integrating over X alpha S lambda of E alpha primed, this has the right signature. Plus, minus, minus, minus. Okay, so there's the Schur classes, and so you get plenty more examples of things that have the Hodge-Riemann property that goes beyond what was known of Gromov and of Bloch and Giese.
Julius, small question. Why this class is not represented as like a product of Kähler classes, like in the previous example? Why it's a new example?
Let me do that. So let me do an example for you. Let's have example. I think this is the simplest example I can think of for that. So let's suppose L1 and L2 are ample on dimension of X is 4. All right, different ample line bundles. And let's just put E as L1 plus L2. And then I need to work out for you what the first Segre class of E is. And it turned out to be this. I hope I get the numbers right. It's C1 of L1 squared, plus C1 of L1 L2, or C1 of L1, C1 of L2, plus C1 of L2 squared. I think that's right. I'm concerned that I've missed a factor of 2 in there, but it won't matter for what I'm going to say. Okay. So the statement is, since this is, if these are ample, then this vector bundle will also be ample, right? And so the statement is that this particular Segre class, that's a 2 class on a 4-fold. So this is lying, has the Hodge-Riemann property. And then to answer your question, let's look at this, right? So this has the Hodge-Riemann property by classical stuff, right? Same with this. And then Gromov gives that this one has, right? And that's fine. So each of these 3 pieces have the Hodge-Riemann property. But if you think about it in terms of the bilinear forms, the bilinear form of this is the sum of these 3 things. And signature is not preserved under taking convex combinations, right? So there's no reason to think that if you just randomly take 3 classes with the Hodge-Riemann property, you get something with the Hodge-Riemann property. And so I think that answers your question, right?
Thank you.
Yeah, and I mean, in fact, we have examples where convex combinations of things with the Hodge-Riemann property do not have the Hodge-Riemann property. So you can't just deduce it from Gromov. Okay, great. Thank you, Vanya. All right, so let's give myself a little bit more space. And let me just comment on sort of some motivation. So where did this sort of idea of looking at the Schur classes come from? And there's some older work of Fulton and Lazarsfeld who say this. They say if you've got a partition of length D, now not D minus 2, and E is ample, then if you integrate the Schur class of E over X, so if this has length D, then that dimension has X, dimension of X is D, this is a number, they say this is positive, right? So they already sort of have a theorem that says if you want to create some characteristic class from an ample bundle, you want to be positive in this sense, then you take the Schur classes. They actually say more than that. They actually say that the only thing you can do is take convex combinations of Schur classes. So somehow the hull of the Schur classes are exactly the things you expect to have this sort of universal positivity property. And so from that point of view, it's natural to look at the Schur classes for this Hodge-Riemann property. And if you think about it for a second, I'm sort of using this is important because, if, the case I'm interested that the length of lambda is D minus 2, let's suppose H is an ample class, then what happens if you integrate S lambda of E times H squared over X, right? So looking at your dimensions for a second, this has dimension 2. So if H is ample, you can rescale, assume it's very ample. So this H squared is cutting this by 2 dimensions. This has dimension D minus 2, right? So this intersection, Fulton and Lazarsfeld are telling me this is positive, right? But this is exactly the thing that I called Q of HH. This is QS lambda V of HH. Right, so Fulton and Lazarsfeld are doing sort of the first step of this. They're saying that this bilinear form that I want to consider, it is has a positive eigenvalue in the H direction, where H is an ample class, right? And I'm certainly going to use this, right? So I use Fulton-Lazarsfeld from now on. I'm going to use it without comment. And in particular, I'm using their result, which in turn relies on classical hard Lefschetz, which in turn relies on Hodge theory. And I'm also going to use the classical hard Lefschetz and Hodge theory, right? So everything I say will depend ultimately on, Kähler geometry and the Hodge, the classical Hodge-Riemann bilinear relations and Hodge theory. Okay. Check the time. Okay, so that's my main statement. And what I can do now is I can give you sort of 2 or 3 kind of variants or improvements of these statements that I think are interesting. Right? So it's not just the short classes I can talk about. I want to make a definition for you. I don't know other places this definition's really come in, but I'm going to define something we call the derived Schur polynomials. So I'll call them, denote them by S lambda of I, so the I being some sort of derivative, just by saying if I think of this as a polynomial, a symmetric polynomial in E pieces, and you replace each of the variables by just adding a dummy variable t, and of course you get an expansion. When t is 0, you get the usual Schur polynomial. They're going to then be some coefficient in front of t, some coefficient in front of t squared, etc. And I use those to define these polynomials that are going to be of lower degree, right? So what was I going to write? I was going to say, so in terms of a vector bundle, S lambda of I of E, this is in a smaller cohomology class. Oops. As you go along this this expansion, the polynomial gets 1 degree, the degree of the polynomials gets smaller. Okay, and so then again, the theorem is pretty much the same. If I allow myself a larger partition, and again an ample vector bundle, then this derived Schur polynomial, or this derived Schur class of E, also has the Hodge-Riemann property. So that's an improvement. And I just wrote down for you some of the polynomials that appear in this way. So I think in the previous slide, I wrote for you this middle Schur polynomial as C1, C2 minus C3. And you can work out what this expansion's got to be. And so the first derivation is this particular combination of C2 and C1 squared. And the next derivation is this particular linear combination of C1, right? So it's, this one involves C1, C2, and C3. The next one just involves C2 and C1 squared, and the next one could just involve C1. And that's going to happen all the time when you have these derivations. But these are different linear combinations of, the Chern classes. So we're getting new examples of Hodge-Riemann classes this way. And again, you could do it for just the Chern classes. If you do something with just the Chern classes, the derived ones are then just the lower Chern classes up to some coefficients. Right? So if you do this with the Chern classes, you just get lower degrees Chern classes. Very good. So those are the sort of the 2 main results for ample vector bundles. And everything I said so far, I think I even used the word projective X. Everything assumed X was projective because it was all to do with having an ample vector bundle. So of course, if you have an ample vector bundle, its determinant is ample, so you're automatically projective. Right? So everything there was in the projective case. But you can ask, are there versions of this that hold in the non-projective case? And that we have. So let me just start with a very quick Kähler version. So now suppose X is not necessarily projective. There's a compact complex manifold of dimension D, and I have some number of Kähler classes on it, right? So distinct Kähler classes. Then what I can do is I can take this S lambda of omega 1 up to omega E, where I think of that as just a polynomial, symmetric polynomial in omega 1 up to omega E. If I just expand this out and monomials, and I just replace product with wedge product. So as long as I guess if lambda has again length d minus 2, the conclusion is then this has the Hodge-Riemann property. Right. So of course the vector bundle here is missing, and projectivity is also missing. Right. So it's really about these particular Kähler classes. So that's sort of our first non-projective version. So we spent a long time stuck on proving that. And it's related to something else. I'm going to write this again. Kähler version, there's also a linear algebra version. All right, so you may or may not be used to thinking of positive forms in a vector space, but suppose you, instead of a vector bundle, you just have a single complex vector space of dimension D, of dimension D. So there's a notion of what it means to have PP forms on a vector space. And so you can even have what it means to have a positive PP form in a vector space. And you can consider this quadratic form. So then this quadratic form, I'll let Q of alpha alpha primed be taking alpha wedge alpha primed wedge this lambda. So S lambda of omega 1 up to omega E. That's a top degree form. So that's not a number, but you can divide it by the canonical volume form on E. Right? So I have a complex vector space. Think of it as having bases dz1 up to dzn. Then you have a volume form dz1 wedge up to dzn. So this is going to be a whatever dd form divided by a dd form. Again, so mod lambda is d minus 2. So here alpha and alpha primed are 1, 1 forms on E. So then this thing has the right signature. Very good. So that's the Kähler version. That's the linear algebra version. So you may think, okay, this is kind of a stupid thing to write down. You do all this work and you get some piece of linear algebra. And originally I was kind of inclined to agree, but these two things are very closely connected, right? So it's not hard to convince yourself, that this theorem implies this theorem. What you do is you just say, I have a vector space. Maybe I let X be a torus of the dimension D, and I take that vector space to be the tangent space at one point. And then if I have these positive 1, 1 forms, I can just move them by parallel transport around the torus. And I really do get Kähler classes on the torus. So if you know this Kähler version of the statement, then you get the linear algebra version of the statement. So that's sort of maybe not such a surprise. But what's also true is kind of this direction is also true. And I think Gromov essentially noticed this, that if you understand this linear algebra version, then using a little bit of Hodge theory and the DD-bar lemma, you can prove this Kähler version as well, right? So these two things are sort of almost equivalent. And the only way I know how to prove it, I mean, so the nicest proof I think would be to prove this just using linear algebra and then to get this Kähler version, but that's not the proof I know. I'm not able to do that, right? So the only way I can prove this linear algebra statement is with sort of this statement here. And the only way I can prove that statement there is with Hodge theory, right? So I've got to use kind of everything I know, positivity, all of Hodge theory and Hodge-Riemann bilinearations to get this linear algebra version. And I don't know if there is a quicker or more direct proof. And even this Kähler version, how do I get that? Or maybe I'll have time to talk about it at the end. I've got to use projectivity at some point to do some approximation. So I've got to use kind of everything I know to get this linear algebra statement. So whilst I'm thinking what I want to say next, would anyone like to ask anything? Seems okay.
No question in the chat, so all good.
Okay, great. I've got it open, but okay, good. So so I won't try to talk about the proofs yet. I'll push off mentioning the ideas of the proof of these statements. At the end, I want to talk about one collection of applications of this that I find exciting, which I just call about various inequalities. So suppose I've got one of these classes, HR of X, Hodge-Riemann classes, and remind you that this is the bilinear forms, this is the signature. So I know in particular, I was always assuming that Q lambda, so Q omega of HH is positive, but H is some positive class, let's say some ample class. Say, right, so it has this positive direction. So, okay, as I expect many of you know, if you have this setup, you have a Hodge index theorem. Right, so this says that Q omega of alpha alpha times Q omega of HH is bounded from above by Q omega of alpha H squared. So this is just a formal consequence of having this particular signature. So the picture you have in your mind is you have some cone on which Q is positive. And then if you take so H is maybe in here somewhere, right? Because Q is positive on that cone. And then if you take the orthogonal complement to H, so where that's the primitive, where this thing vanishes, so you have this space. This is the set where alpha such that Q of alpha H is 0. Right, then Q is negative definite on this space here, right? So sort of a standard picture of what the Hodge index theorem looks like, right? So i.e. Q omega is negative definite on the set of alpha where Q of alpha H is 0. So in particular, you could apply this where omega is some Chern class or some Schur class of some ample vector bundle, and you get some inequality that maybe is not such a surprise if you're used to the Hodge index. Okay, so this would be some, maybe I take omega, so e.g., let's take omega to be CD minus 2 of E, then we're getting that if you integrate alpha squared CD minus 2 of E, integral alpha H CD minus 2 of E, that's bounded by, I made a mistake, sorry, alpha H squared, that should be alpha H CD minus 2 of E squared, right? So this is some inequality to do with just that particular Chern class of E. I think that's interesting in itself. But actually you can do something else. So a little twist on that story is the following theorem, that again, if E is ample, then you can compare these particular Chern classes. So here I've got some characteristic class depending on the D minus 2 Chern class. And here, instead of D minus 2, I've got a D minus 1 Chern class. And here I've got a D minus 2 and a D minus 1. So this is intertwining different Chern classes of this particular vector bundle. It turns out there's a factor of 2 in here. I can even tell you what happens for equality. I won't write that down. So as the rank is large enough, you can only get equality if alpha is 0. All right, so here's the interpretation of this. So the interpretation is, okay, this is meant to be the same primitive space I was talking about before. Okay, so this term here will be positive by Fulton-Lazarsfeld. This term here is strictly positive. So if this term here is 0, right, so you're in the primitive of CD minus 2, then this thing is negative definite. So that's just what I told you before, right? So I have the same picture of my Coulomb, I have my H, then this primitive here is just given where this term vanishes, right? But this inequality tells you more. It's saying also there's a subspace where this term vanishes. So that subspace is also of codimension 1. So there's some other subspace. This picture gets a little bit busy. So this is maybe the set of alpha, such that alpha CD minus 1 of E is 0. CD minus 1 of E is 0. Let's fix that. And it's saying that this, this bilinear form taken where you integrate against CD minus 2, it's also negative definite on this blue space, and those could be different. So it's giving you more information than just the Hodge index theorem. And it's interesting, I think, in its own sake, and it turned out to be extremely important for kind of all the proofs we needed to make happen. And let me just, I won't really say, but the idea of the proof is to say, okay, how can you get something that involves sort of the D minus 2 Chern class of E and the D minus 1 Chern class of E, where it's a trick, you take X prime to be X cross P1 and take E primed to be E tensor OP1 of 1. So again, if E is ample, this tensor product will be ample. So I can apply the previous work, and so I can apply sort of just the Hodge index, usual Hodge index from the previous slide to the class. I guess it's CD minus 1 of E primed. Okay, so there's not much more to it than that. You just have to manipulate that around. But if you look at this for a second, what's the D minus 1? I mean, the numbers are made, right? This has 1 dimension higher. So this thing here is codimension 2 on this space. So the Hodge index applies. And what happens if you work out the D minus 1 Chern class of E primed? Well, you get terms that include the D minus 1 Chern class of E and another term that involves the D minus 2 Chern class of E, right? So up to sort of just manipulating and doing some formal things, that's the idea of the proof. And this works exactly well to give this sort of stronger and new inequality. So that was my favorite inequality, but now I've got more, okay? So you can do something even better. You can do something that mimics the Curvancy Tessier inequalities, right? So here's the theorem as I've written. So suppose E is ample, vector bundle on X, and H is an ample class. So you can consider just, the most natural thing to consider in terms of characteristic classes, you take the ith Chern class of E, and then you wedge it with enough copies of H to give you a number and integrate over X, right? So for each I, you get a different number, right? This way, of course. And the statement is that this is log concave as a sequence, right? So log concave means if you take the logarithm of this, you get a concave function in I, right? Or another way to say the same thing is if you think of this sequence, you can consider 3 consecutive points as the ith one, and then around it is the I minus 1 and I plus 1. And so if you take the product of the I minus 1 and the I plus 1, that's bounded from above by the I1 squared. Right? That's just another way of saying that this thing is log concave. So that's a version of the Curvancy-Testy inequalities. So let me just say CF. The Curvancy-Testy inequalities say the following. They say if sort of A and B are ample line bundles, then if you take I goes to integral of C1 of A to the I, C1 of B to the D minus I is log concave. So I hope it's clear that's the same sort of idea, right? You've got sort of, here we've got 2 ample line bundles, some sort of characteristic class built between them that depends on I, and then you get log concavity. And here I've done the same thing, only I've got a vector bundle. And in fact, it's not really hard to show that this theorem here implies this Curvancy-Testy thing. You don't quite take E to, I thought initially, I think you were going to take E to be the direct sum of A and B. It doesn't quite work like that. But it's something like you scale up A so that it's globally generated. And then you take E to be, well, I think the kernel of the evaluation map is not going to be ample, but its dual will be at least Nef, right? So it's not so hard given an A and a B to cook up this E, and so that this thing implies that thing. So it's sort of a higher rank version of the Curvancy-Testy inequalities. And I wrote it that way because I think it's clearer, but these are about Chern classes, my talk's about Schur classes. And so it's the same statement here. If you have, I guess the partition has to have size D for this to make sense. You take this characteristic class here where the ith one is the ith derived version of the Schur polynomial. So that gives your polynomial a class in a particular cohomology class. You wedge with enough h's to get a number, and then this is log concave. Right? So this really is a generalization of this, because these derived ones end up being the Chern classes for a suitable partition. I'm going too fast. I have an hour, don't I? Oh well, I'll be done well. I'll be done well before.
Yes, an hour. But
I'll figure things to say. All right. I was worried I wasn't going to be able to say everything I wanted to say. Okay, it's good. So these are these sort of, and these convexity things are kind of very important and very interesting. All right, and sort of known for the algebraic geometers. Let me give some more examples of this. This is the case. I gave you a case where we just have one ample vector bundle. I can do more. So suppose you have 2 ample vector bundles, right? Which could happen. And suppose I've got 2 partitions with their sizes being large enough, or the sum of their sizes being large enough. I can take this characteristic class. So I can take some Schur class of F, or more precisely, some derived Schur class of F, and then some other derived Schur class of E. And then if you believe me, I've got these numbers sort of just balanced, so that if you multiply these 2 things together, you get a top degree form on X. Always the dimension of X is D. So I've now again given you a number, and again, this thing is log concave. So maybe that's the strongest statement I can give about some sort of log concavity statement for these ample vector bundles, and it proves all the things I've already said. And that's kind of nice. I like that one. And here's a question that I don't know how to answer, but I'm not sure how hard it is. So what about sort of more ample vector bundles? So say you've got 3 ample vector bundles, then I guess you're going to get some number of classes that will tend not just I, but depend on I and J, right? I guess there are probably many ways of doing this. You have some sort of 2-dimensional grid of characteristic classes you can define using Schur and derived Schur things. And then, okay, so I've made that vague, but what about this? So log concavity is usually a function of it's a statement about functions of one variable. So I'm guessing you need to package up this sort of two-dimensional array into some sort of matrix that has some sort of positivity property. That would be my guess. Or maybe a more advanced way to say this is this idea of Lorentzian polynomials, where you can package up various numbers and give some sort of generalization of log concavity, right? So I don't know exactly what the answer is for this. I do feel like what do I can say? If I knew the statement, I feel I could probably prove it, right? Somehow I think it's finding out the statement that that's harder than actually the proof, right? Okay, very good. And okay, this was all a statement about vector bundles. Here's something nice. You can make statements. This has consequences for just polynomials, symmetric polynomials. So let me give you an example. So let's have, for example, so here's a corollary of what I've been saying. Suppose x1 up to xe and y1 up to yf are positive real numbers. Probably 0 is fine. Maybe strictly positive is better. And then let's consider this thing here where you take the ith derived polynomial of mu and plug in the x's to it, and you multiply that by some derived polynomial of lambda. I've got to get the numbers right. Of y1 up to yf. So for each I, this is a number. So in principle, you could work this out, right? Given any partition, you can work out this derived thing. So this is some symmetric polynomial in the x1 up to xe. And this is, again, some symmetric polynomial in y1 up to yf. So of course, if you're fixing these numbers, then this is a number. And the statement is that this is log concave. Very good. Okay. So, I mean, so why is this? Okay. So why does this follow from the previous thing? I mean, the proof is just, the proof is, you just put sort of E is equal to, I'm sorry, I think you've got to work on some product of projective space, and you do something like O of x1 plus O of xe, F being O of y1 plus O of yf on sort of P1 cross P, I don't know what to call it, Pn1 cross Pn2. So you just apply what I've said to this very simple product of projective spaces and this particular vector bundle. Okay, so I'm cheating a little bit because if these are real, you ask yourself what this means. It doesn't really matter. Make those rational, make those integer just by scaling. So assume these are integers. These are two perfectly good ample vector bundles on this particular project, on this particular product, and then you use this sort of log concavity we had before, and you get this statement about just purely about polynomials. I can make that simpler. So for example, you can do another thing. You could say just I goes to S lambda I of x1 up to xe is log concave. That might be the simplest statement about polynomials that I can make. Okay, so what to say about this? First, most important thing to say is I'm not an expert in symmetric polynomials. Many people are. So I don't know with 100% certainty that this is not previously known. I've looked, I haven't seen that exact statement. There's lots of statements that connect Schur polynomials to convexity and concavity. That's certainly true, but I wasn't able to find this exact thing. It might be that it is contained in one of the statements I saw, but I couldn't find that, or maybe more likely easily derivable from some known thing. That I think is perfectly possible. But I do know one case, there's a special case. You can replace S lambda of I with the symmetric polynomial, Ci, so I is symmetric polynomial. So then this is a classical thing. If you take the symmetric polynomial and these positive things, this is log concave, and this is due to Newton, 1707. There you go. So Newton proved this statement about symmetric polynomials. In fact, he proved more. He said not just this is log concave, but something that he calls that is now called ultra log concave. So it's an even stronger form of concavity where you put some sort of binomial coefficients in it. So he has a much stronger statement. And this, yeah, so that's sort of fascinating to me. And when I was preparing for this talk, I thought about that again. So that ultra log concave is not true for Schur polynomials, right? So in some sense, I don't really reprove, the statement as strong as Newton had it. On the other hand, it might be that you can strengthen this somehow. So I don't know how to. It might be you can strengthen this somehow. So it's true for all Schur polynomials and derived Schur polynomials and gives you Newton's statement. That would be interesting. Or it might be that you get some amount of concavity for the Schur polynomials, and then for some reason I don't understand, you get like more for the actual symmetric polynomial. But when I say symmetric polynomial, I mean elementary symmetric polynomial. And so maybe the elementary symmetric polynomial has more concavity or more positivity for some reason I don't yet understand. Anyway, so that's my generalization of Newton's statement. All right, so as I said, I've rushed through this. I'm going to take just the end of the time that I had planned to talk to you about the proof, right? So the proof of the main theorem, or at least the first main theorem, is this. So we've got an ample vector bundle of rank E on a projective manifold of dimension D, and we have a partition of length D minus 2, and the goal is to show that this Schur class has the Hodge-Riemann property. All right, so it's done through a number of steps. So let's say step 1. So step 1 is let's assume the rank of D, or the rank is, which is E, is D minus 2. And let's do this for the Chern class. You want to show that CD minus 2 of E has the Hodge-Riemann property. So this would be a particular case of this statement for a particular partition. Okay, so what do we know? So I told you 20 minutes ago that Bloch-Giesecke tell me that this has the hard Lefschetz property. So if you take its associated bilinear form, that bilinear form is non-degenerate, so it doesn't have any zero eigenvalues, but it doesn't necessarily have the right signature. So what you do is you run a continuity argument. So you replace E with, well, essentially E tensor, okay, let's fix an ample class H. E tensor O of TH, where T is real and positive. Okay, so this you can't do because this doesn't exist as a line bundle, but I don't really need the vector bundle to exist. I just need its Chern classes to exist. Right? So you don't really do that. You do E of what's called TH, these sort of R twisted things. And this is sort of some formal object, R twisted bundle. So the bundle doesn't exist, that does not exist as a bundle, but its Chern classes do. Its Chern classes Ci of E of TH do exist. By which I mean I just define them to be the thing they would have to be if you're really thinking that this is a twist. Right? So it has some Chern classes, and the Bloch-Giesecke still applies here. So Bloch-Giesecke, this tells me that this bilinear form that I'm interested in, not of E, but of E twisted by this TH, this is non-degenerate for all T, I guess positive. Positive or bigger than or equal to 0. Let's say bigger than or equal to 0. So it's non-degenerate. I mean, you've only added positivity when you do this twist. Okay, then you ask yourself, okay, so what this means is you have this bilinear form, this matrix, it's non-degenerate, so signature doesn't change as T varies, right? Because it never picks up a 0 eigenvalue. And then what happens when T is very large? When T is very large, I mean, this term here will just have some term that looks like T to the D minus 2 times H to the D minus 2, right? So, and C D minus 2 of E of TH looks like T to the D minus 2, H to the D minus 2, plus lower terms, what's lower than d minus 2, d minus 3. And so if t is getting very large, it's this term that dominates. And so the classical Hodge-Riemann bilinear relations tell me that this has the right signature when t is large, and then Bloch-Giesecke tells me that the signature doesn't change, right? So Q, let's call this QT. So QT has signature plus minus minus for t large, and hence for all t. Particularly when t is 0, which is the thing I wanted, right? So this continuity argument and the Bloch-Giesecke gives me this statement here, okay? And then just to be clear, again, what have I done? I've used Bloch-Giesecke. I've used it not just once, but I've used it kind of for all t positives. I've used it an uncountable number of times. So I've used, again, Hodge theory an uncountable number of times. Okay, so that gives me this first step that works for that particular case. The second step is I'm going to pull a rabbit out of a hat here. If you know this, then you'll know. Okay, so if you don't know this, there's going to be a little bit of just some machinery. Is that Schur classes were originated as degeneracy loci, and so you can essentially realize them as effective classes. That's not quite right, but what I can say is that Schur classes are push forwards. So push forwards of Chern classes. They put that in inverted commas. It's not meant to be precise, but the precise statement, and this was used by Fulton Lazarsfeld and discussed by Fulton in various papers, is to say there exists an irreducible, say C going down to X, the dimension of C is N, and a vector bundle Q of rank N minus 2, so that, let's call this map pi, so that if you push forward Cn minus 2 of Q, you get the Schur class of E. Okay, so I'm not telling you what this is, but maybe I'll just point out what is C. C sits inside some projective bundle associated to E via some vector space going down to X. So V is a vector space. And Q is the tautological bundle on this projective bundle restricted to C. Okay, so I'm sorry if you don't know that, and I'm just pulling this out, but let me point out what this gives you, right? So you may think, okay, this gives you everything, because step one was to prove that this had the Hodge-Riemann property, right? And then if you push forward, that does preserve the Hodge-Riemann property nicely, so you win everything. But there are kind of two subtleties here, right? The first subtlety is that C isn't smooth, it's just irreducible, right? Okay, you pass to a resolution of singularities, you're still going to lose something. But worse than that, the tautological vector bundle on this projective bundle is not ample, right? It's only a limit of ample things, it's only Neth, right? So then as Q is Neth, so in some sense a limit of ample vector bundles, this doesn't give the statement I want. It just gives that the Schur class of E doesn't have the Hodge-Riemann property, but it lies in the closure of things that have the Hodge-Riemann property, right? If I move Q a little bit to make it ample, then I win the game, but that's not the thing I actually wanted, right? I wanted to get actually the Schur class of E had the Hodge-Riemann property. So again, in terms of this bilinear form, we have one eigenvalue that is strictly positive, coming from this ample class H, and then all of the others, I guess, are less than or equal to 0. Right? So there could be some negatives, but there could also be some zeros that I need to rule out. So you get sort of without too much difficulty that you're in the limit, this sort of weak Hodge-Riemann property. So maybe I'll call this weakly Hodge-Riemann. All right, good. And now once you've got step 2, you ask step 3, how do you put this all together? And this is always going to be a bit tricky, right? You've got something where you know, I mean, whenever you've got some quantity that you know is bigger or equal to 0, and you want to show that it's strictly positive, you're going to have to do some work, right? And that's exactly what happens here. So of course, everything I've done is universal. So it applies not just to E, but it applies to E if you perturb it a little bit. So let's apply E. Let's apply step 2 to the vector bundle E, again, twisted by some TH, where say mod T is small. So you just move E a little bit, at least formally. And so now what do you have, right? Well, you've got some bilinear form depending on T, and you know that it always has the weak Hodge-Riemann property. So in particular, let's look at what the Schur class of E of TH is what. So when T is 0, this is of course just the Schur class of E. And then what do you have as its leading order term? Well, by definition, it was the derived Schur class of E, etc. Or said another way, the Q S lambda of E of TH is the Q of S lambda of E plus T. So I'm sorry, this is times H times this Q S lambda of 1 of E of H, etc. Right? So now what do we have? So we have a family now of bilinear forms, all of which have this weak Hodge-Riemann property. And you know that its derivative, right? You may hope, well, we're going to do some sort of induction on the dimension, right? So maybe you've proved the result for one dimension smaller. So maybe you know already that this thing here has the Hodge-Riemann property strictly. So you have this family of bilinear forms, all that have the weak Hodge-Riemann property and whose first derivative has the actual Hodge-Riemann property. Maybe that's enough, but it's not, right? So even that's not enough to do it, right? So induction by dimension. So you need even more. So the ingredients are to do this. And the ingredients of this step 3 is to do the following. So the first is you do perturbation, E of TH, let's say T is small. Right, the second is you've got some sort of induction on dimension of X. And as I said, it's not a general statement that if you have bilinear forms of this particular kind and you understand their derivatives, then you can augment from the weak Hodge-Riemann to the Hodge-Riemann property. But we know more. We know these sort of Curvancy testy type inequalities that I talked about. Right? So also 3, then you use the sort of inequalities previously discussed. So those I do know hold simply, I mean, those are inequalities, right? So being the limit of Hodge-Riemann means those inequalities still hold. So now I really do have a lot, right? I have these families of bilinear forms that have kind of all of these properties, right? I understand what's happening under perturbation. The leading terms have got some sort of induction, and then each of them themselves have these kind of inequalities. And what Matej and I have done is we've just developed this sort of linear algebra machine that says if you have these kinds of families of bilinear forms with these particular properties and the weak Hodge-Riemann property, a process that, for use of a better name, I call augmentation. But it is just linear algebra. This gives you that S lambda of E is actually Hodge-Riemann, not just weakly Hodge-Riemann. And so this machine, I think, can be used to, you know, to go from something being just weakly Hodge-Riemann to strongly. Okay, so that I won't sort of go into that. I mean, it's not some triviality. It's like 4 or 5 pages of bilinear forms. You have to abstract what all of these things are, and then just work with the bilinear forms themselves. So I don't really have any understanding what this is, other than it works as long as you have these particular properties. Okay. All right. You know what? I think I'm gonna end there and say thank you very much and take any questions. Thanks.
Thank you, Julius. Let's thank Julius for a very nice talk. Thank you. And in Zoom. Question, please. Questions.
Hey, Sebastian.
Okay, I already asked my question during the talk. So, in general, do you expect more classes?
Yeah. Yeah. So I could talk about that for a long time. Okay, so I think the right question is to say which convex combinations of Schur classes have the Hodge-Riemann property, right? I think that would be the sort of perfect answer to Gromov's question, or whatever, you know, the right answer. I don't know the answer at all. So what do I know? I know I have some regions so there's a simplex, I guess. So I have some regions where I know this holds, so certain convex combinations I can prove. I can also have examples that show that not all convex combinations hold. And I have maybe some conjectures of what might happen for the triangle where you have just 3, but I can't prove them, right? So somehow I don't think it's helpful for me to write down these partial statements because they're not so helpful. It is a really interesting problem, and it is very closely related, if not, I mean, closely related, if not exactly the same as the following thing. You take the Grassmannian and you ask which convex combinations of Schubert, what are they called? Schubert cohomology classes can be represented by an irreducible variety. So this is something Azet and I have talked about, and it seems to be quite a hard problem, right, to work out that sort of thing. And I think these problems are very, very much related.
So this is not known, no?
This is not known, and we've spent some time, and it seems to be really hard, right? I mean, give me some techniques. I have no technique to show. I mean, essentially, the only thing I can do is Bertini, right?
Yeah.
So we made some progress with Bertini, but not something that was clearly the full story.
I have also historical questions. So Newton paper, you mentioned the result. Did you find it really in Newton work or something?
No, but I found it just reading about log concavity of, I mean, he also expresses it different. It's like differently. It's like you've got a polynomial in 2 variables or something. And then it's about what happens with the roots of these, right? Or something like that. So yeah, no, I didn't.
It is log concavity, yeah.
And it has, yeah. So no, I don't just read papers from 1700.
Okay. Thank you, Julius. So any other questions? If you want to ask a question to Julius, please ask now. So okay, if no, let's thanks Julius again. Thank you.
Thank you very much for your time. Thanks everyone for coming.
Thank you, Julius. It was very nice to see you again.
Yeah, great to see you. Enjoy Miami.
Hopefully one day we meet in person again. You see, in-person conference already started, so it's yeah. But people now, I know some people told me during this week that we're a little bit afraid of giving in-person talks. People forget how to do this.
I have given one, yeah, since 2020 or something. Yeah, but I mean, you're teaching in person, so it's not so.
Yeah. This is.
You remember what the whiteboard is, right?
Yeah.
How to take the cap off the pen.
Yeah.
The basic things.
Yeah, this is true, but.
No, but I mean, teaching in person for after pandemic, did feel strange, right?
Yeah.
We remember how to do it.
Yeah. This is true. Okay.
Okay, good. Thank you both for taking the time to do this and moving stuff around. By the way, did you get the one that I hosted? You got the video and everything for that. I didn't do anything.
The problem is like this. I'm from the United States. I cannot log in into Zoom account because of security things. Zoom believes that I should be in the UK. So I think
how long have you been in the US now?
I mean, since Friday.
Oh, I see. Okay.
It's Friday. Yeah, I will do this once.
I just wanted to make sure it worked. Okay, but I mean,
I'm actually trying to discuss with Jesus, so he will check. But Jesus on some vacation this week.
Yeah, it's fine as long as it works. All right, nice to meet you.
Hopefully it's okay. Hopefully it's okay.
Awesome. Speak to you soon. Bye-bye.
Bye.